I'd like to welcome you to this International Society for Behavioural Nutrition and Physical Activity webinar. Today's webinar is hosted by the Network of Early Career Researchers and Students, also known as NESI, and today's topic is on physical activity, data processing and visualization. Myself, Emma Lawlor, and Teferi, we are part of NESI and we'll be moderating this session. So just very quickly, it was just to highlight that throughout the year, there's many webinars going on through ISBNPA, such as the NESI ones and also the special interest groups, and these are also available on ISBNPA website to view. We're also using Zoom today, so you're muted by default as well, but we would like you to put any of your questions in the question and answer box at the bottom, and at the end of the session, we will use these to ask the presenters as well. And next, it's over to Teferi.
Today's webinar is on physical activity, data processing, and visualization. And we're very happy to have two great speakers with us today, Dr. Mackintosh, Associate Professor at Swansea University, and Dr. Tom Stewart, Senior Research Fellow at Auckland University of Technology. We will then have time for question and discussions with the speakers. First up, Kelly will discuss the power of co-design for physical activity. What is Play-Doh got to do with it? If you would like to take it away, Kelly.
Okay, thank you very much for that introduction. So yes, today I'm going to be largely looking at co-design of physical activity. But just to give you a little bit of a background, I'm currently based in Swansea University, which is part of the UK and based in South Wales. And that picture on the bottom left is our buildings, which hopefully one day and this year we may actually be able to continue and actually go into work again. So in terms of my personal background, I work in two kind of areas. One is the measurement of physical activity, and the other one's actually intervening and trying to promote physical activity. But within that particular area, the key challenge there is technology. We know that tends to make you maybe more sedentary or more inactive. But despite that, especially when you work with children, they're really reluctant to relinquish this type of behaviour. And on the other hand, if we as researchers are debating what actually constitutes physical activity, how active do you have to be, what is 60 minutes, should it actually be 60 minutes of moderate to vigorous physical activity, how can we really get children to understand how active they need to be? A lot of my earlier work, as I said, worked on more of the measurement angle. So really trying to look into the energy expenditure associated using various different things such as machine learning, which I'm sure Tom will pick up on in the second talk today. But what strikes me is the way that we actually interpret data. So as scientists, we start to look at visualizations. We're essentially always looking for patterns in data. And even when we look at machine learning, what we're trying to do is really pull out that information. So building on from maybe quite a long time ago when we were looking at cut points to then starting to look at energy expenditure, we actually want to look at what types of movement we're doing rather than always just focusing on the quantity of physical activity. So for example, if you're doing this particular movement here, you may get this type of pattern that comes out of the data. But of course, one of the things that always resonates with me is, yes, we're looking at visualization and we want to interpret it, but how do we make that more transparent and how do we transform that in terms of getting people more active? Even when we start to do analyses, such as compositional analyses, this is great in terms of visualizing what we need to do as researchers. It gives us context around what's the optimal trade-off between sedentary behavior, sleep, and moderate to vigorous physical activity for a specific outcome. So in this case, in cystic fibrosis, maybe we're looking at lung function. That gives us the context in terms of how we want to promote physical activity, or what's the overall compromise in terms of how we promote it. But it doesn't necessarily translate to how active people need to be and how they relate to their activity. So for me, the challenge is actually translating really complex data simply. to get people to understand what they need to do, and then hopefully translate that into behaviour change. So with this, when I first started at Swansea, we're actually housed within the College of Engineering, and that for me opened up lots of different opportunities. And in fact, that was my first short-term postdoc coming to Swansea, was to really build on those engineering networks. If I look back to some earlier research by Paul et al., they find that when you try to get children to access web platforms, for example, to gain feedback on how active they were, they wouldn't regularly access it. So it had to be something that was easy for them to see. So with that in mind, the first thing we actually looked at was glanceable displays. So a simple way that children can gauge and gain feedback from it. Now, this is actually where the first co-design works started to be embedded. We worked with children to get them to think around what kind of theme did they want. In this particular case, they wanted it to be Mission Possible. It was a secret agent theme where they spoke around somebody that was a free runner that hacked into the school system and set them Monday morning missions. They would then be put into different colour teams based on the colour of Fitbit they got. They would go out, they'd perform these missions. And then when they came back into the school, it synced through the school's Wi-Fi system and visualised the data on the LED strip. The thing that they wanted to show was, if they're in the pink team, the length of that pink LED strip was how long they'd been active for, and how fast it flashed was the intensity. And what you can see here is that children found it really enjoyable. They didn't need as much encouragement. So even those children who don't like PE or sport, they found it that they wanted to enjoy it because it was a game. It was fun for them. But one of the things they did come back with was saying that they liked it, but it wasn't something that they could keep. They wanted to keep it and be able to show other people it. So that got me thinking a little bit more so. So we took this feedback from the children and thought, what is something you can keep that shows how active you've actually been? This actually brought me into the work that's done by Rowan Coates in the Exergain lab in Melbourne. What we'd previously done was that near real-time feedback. But with 3D printing, you can actually look at delayed feedback. So their work looked at converting heart rate into some kind of patterns. But what we really wanted to do is, well, what kind of tangible object do children actually want? So this is where we started that iterative co-design process. Now, I know there's a lot of early career researchers and students listening. One thing I would say is never be afraid to push things and think outside the box. I had one of my PhD students who came to me on this project and said, okay, I think we should use Play-Doh for this. And I have to admit, I've never used Play-Doh before in research. But with this particular example, I thought it was a really creative way to engage children and gain feedback in terms of how they visualize physical activity. How would they actually relate to what they are doing and what movement actually is? Now, with a colleague, Dr. Melita McNary, back in, I think it's 2017, we did an ISBNPA workshop, and we actually got members to do this task. I will leave you to think about the Play-Doh models that they came up with, and I will move on to what the children came up with. So what children came up with was showing something like, for example, a star, which had 7 arms, one for each day of the week, and the bigger the star and the longer the arms, the more active you were. All the way through to a face, which unfortunately, if you were bald in this child's eye, you were unhappy. But if you had a lot of long hair strands for each day of the week, you were very active and had a big smiley face. When we go to adolescence, they were slightly less creative because essentially they liked bar charts. They did have different hobbies such as paddleboarding or gardening, for example. But essentially it really was visualizing the data in that graphical format. Following this process, we actually converted those models from the Play-Doh using computer scientists to create different models. At this stage, we then fed them back even more so to a large sample of children at the British Science Festival. So this saw over 6,000 families coming through. And from that, we gained feedback in terms of what their the preferred model was. But we also got some qualitative feedback from this as well in terms of how they interacted with it. and what they thought of that particular model. Again, this is a project that I was challenged on. So a colleague from Australia was over and questioned at that point, why would you then do an intervention if you don't know if the children actually understand the models? So we did an extra study that then got children to interpret the models and gain feedback on how we needed to change the design slightly. And what happened from this was, for the primary or elementary school models, we looked at this almost sun model, and the new addition was actually this target bar that put in what the government guidelines were, where we actually need them to be. But we also added in the blob here that distinguishes between moderate and vigorous activity. So essentially you want longer arms with the blob towards the end of the arm to try and improve that across the time span. And for the secondary school, similar process, but again, it's the depth of it here. So here would be the thickness, would be the vigorous activity, and the rest of the time was spent in moderate. Following this, we then took it on to a short-term intervention more around the feasibility of this particular project. So with this particular one, it was a 3-month fader design because we wanted children initially to gain that feedback, but then see over time if that would translate to the different types of behaviours and they could reflect on them. So children in general would wear an accelerometer for a week, and following that, we would convert their accelerometer data into a model and hand those models back to them. So over this duration, they actually received 4 models, and upon receiving every single model for every child, we actually did a short video interview. And the reason for doing this is we didn't want it to be a subsample. We wanted to gain their immediate thoughts on receiving that model and ask them to talk through that for us. And again, when being asked to put this presentation together, one of the things I was asked to provide a context on was maybe different ways of presenting different types of information and particular qualitative data. So for this particular study, I've adopted something called pen profiles. When I was a PhD student at Liverpool John Moores University, I was lucky enough to work with Professor Zoe Knowles and Dr. Nicola Ridgers, and they had been working on a different way of visually presenting qualitative data. So for example, here, it shows the key quotes, but it allows us to visually see under which kind of themes that falls under. And it also gives the strength of the data in terms of how many children have actually raised quotes within those themes. So from this, you can really see that children were enthusiastic about the models. They find them really cool. They could relate to them, which is a really important finding, that even on that first model, they could say which day it was and how much activity they'd done compared to other days. But by this point, a quarter of children had started to use it as a motivational tool. By the time we got to model 4, the children were obviously still able to relate to the models. But what was interesting here is they really built in that element of comparison, and that was within themselves. So they could compare their models across time and really think about how they change their behaviours or perhaps become more active. And again, we started to increase the number of children that were using them as a motivational tool, but only a small percentage, although positive, were starting to use specific goal setting strategies within their models in order to try and promote their own activities. And lastly for this, the key point to bring across is that they had an increased awareness. They were now slightly more aware of what they had to do. But when we broke this down, this was largely around the secondary school children rather than the younger children. So the key things for this is really the sense that how we can drive this forward, and perhaps going forward, it's the educational component that was missing. So if we can pull on those aspects and maybe not necessarily use them in terms of long term, because perhaps it's not that scalable, but if we can drive that forward and use that as an education as the initial step, then that's a really positive outcome from this. As I say, we were very lucky within engineering to be able to batch print these kind of models, but the scalability is something that could be challenged. So one thing that resonates for me, and I come all the way back, despite doing that whole project, there was one particular child's comment and played a model that really stood out. For a lot of you, you're probably at the point where you're starting to do ECR grant applications, for example, And a lot of the things we're really being pushed on is this blue skies thinking. And I asked you, well, what's actually better than asking a child for what they think? Because the majority of the time, they are far more creative around it. So this example here around this musical piano notes, whereby the higher the note, then the more active you were. That's particularly resonated with me. I'm probably going to give you a little bit too much insight in terms of my kind of films, but it seems a little bit topical at the moment in the sense of we've hopefully slightly refreshed from the festive period. But in The Holiday, for those of you who've seen it, is there a moment where they're trying to almost give someone their own personalized theme tune. And to me, I think, well, actually, how cool is that if you could have your own theme tune in terms of how you move? If we then look at the top kind of rated activities that children do, a lot of them put down that they like to listen to music. And unfortunately, we often do get the scenario where they sit down and listen to the music rather than move to it. So why not use our own body's natural beat, so the heartbeat, in terms of how much we're raising it by moving around more, to translate that into music. Again, if we look at accelerometer data, and you actually pull out maybe one trace of an accelerometer file, that actually translates and looks fairly similar to audio waves. So if we can actually translate that, what we need to do here is go back, and we're starting this whole iterative process again, this time not with Play-Doh, but with different types of musical instruments, and asking children to think about how would you convert music into movement. Following that, the idea is that in the long run, we can actually get children to understand not only the type of movement and the quantity, but also the quality of it. So perhaps if you get a really nice harmony, you know you've done a movement and executed it very well. So I think there's a lot of scope going forwards. Some of the ideas coming out of this are that they almost want it as a gamification approach, whereby they can do a certain type of movement, create a tune, and send it to their friend, who then has to try and replicate it. So the idea there is that they're really starting to understand their different types of movement. Benefit of that is that it becomes more near real time again, rather than having this delayed feedback that we would have with the 3D printing. And again, it's really personalized to them. But one thing I don't think would come through quite as well is really pushing on that quality, and not necessarily from the child's perspective in this context, but more so in terms of perhaps PE teachers, coaches, for example. So how can we ensure that we're actually getting children a variety of movement and these key fundamental movement skills, for example? So some of the earlier work, again, around the measurement angle, was done with biosciences. And the benefit of working with biosciences and animals is the sense that you can put these accelerometers on them and they actually leave them on them. We don't have the battle in terms of wear time. So what you can see here is you have the 3 axes of an accelerometer. And if you have that axis and you move in every single way possible, you get the perfect sphere in this case. And the bigger that is, it's almost the greater the energy, so the further away from the center of the point. Now, if we look at an elephant seal, for example, you can see that they essentially do lots and lots of somersaults, and that's exactly what you visualize there. But if we then move on to a water volt, it essentially does nothing, not a great deal. And unfortunately, that might be the patterns that we see for a lot of children. So how do we take this forward in terms of fundamental movement skills? Well, an example on the left here is actually a basketball free throw. So if you look at the blue area here, well, that's the supporting hand, whereas the other hand is the follow through for the free throw. But it starts to tell us in terms of what kind of movements are actually happening. And that gives us context as a researcher, but it does give us that scope to feed back as well as in any context in terms of a PE teacher, for example. Another example here, so hypothetically, this could be a sea swimmer. So in figure A, you can see 2 strokes. Figure B, you will see the greater pulling because as the hand's going in and out of the water either side. But by the time you get to figure D, you can see they've almost lost that quality of movement. And that would give us that key information in terms of when you'd actually need to pull back and intervene. Now, this is just a very quick example of one of my MSCs who managed to do this in a few weeks, mapping an overarm throw. And you can start to see in terms of what almost the barrier is within that, and what that band is that would mean that you'd be competent in terms of the throw. If you look here, you've got a variety of competent throws assessed by the TGMD2. But if you look at the non-competent throws, you really start to see the variation that can occur. If you plot the means of these, you can actually see really closely with the red line what's actually going wrong in that. But going forwards, what we need to know is, we understand that as researchers, but we need to embed different people and get the real-time data. So one example is we're inundated by wearables, so why not use wearables to give this type of quality data? So we're currently working with Polar to convert this type of quality feedback, so using the heart rate and accelerometry data to then come out with that quality feedback. And again, that particular process is actually going to be that co-design whereby we gain almost the participant information back. And the final thing, just to bring it together, is that perhaps as a society, if nothing else, we can do citizen science, and we might look as a region. So on the left-hand side, we have Italy, and it can show you how active and how that changes across the different regions. So there may also be scope to do this as a society together and pull in that citizen science angle. So just to conclude, hopefully I've managed to get across in a very short time frame that co-design is particularly important. It can give us unique strategies for physical activity promotion. But for me, the key thing here is to really improve that depth of knowledge of people, their awareness of the physical activity levels. A lot of these ideas might not necessarily work in the sense of they have a novelty effect. It's how scalable these kind of angles can initially be. But if we can integrate this as an education tool to at least get people to understand and internalize their physical activity, then that's a really positive stance going forwards. And finally, hopefully I've managed to convince you that combining measurement and visualization to translate that message to participants is particularly important. So like all work, there are numerous different acknowledgements, but I've highlighted a few key people here. Thank you very much for listening.
Thank you very much for that, Kelly. That was great. I'm also, as well, people can put more questions into the question and answer box if anyone thinks of anything throughout. And next up is Tom, and he's going to speak on visualization of physical behaviour data.
Thanks, Emma. Let me just share my screen. Hopefully you can see that. So as Emma said, I'm Tom Stewart from UT University in New Zealand, and today I've decided to present mostly on visualization of physical activity data. But of course, there's a little bit about processing of this data as well, because in order to interpret what you're seeing in some of these graphs, you need to understand where the data came from. But it's only a little bit, nothing too technical. And the focus of my presentation is sensor data, what Kelly touched on at the end of her presentation, and specifically accelerometer data from activity sensors. And on the left here, you can see what the raw data from these sensors looks like. It's literally 3 columns, X, Y, and Z. And what you're looking at here is acceleration due to gravity, which is an arbitrary number. And the goal for us is to turn these numbers into meaningful physical activity metrics and to be able to visualize those and understand patterns. And we have a processing workflow that turns this data that you see here into those metrics that are understandable. So you're probably aware, if you've used accelerometers before, we have 3 axes, X, Y, and Z, as you can see on the right. Some newer models of wearable sensors, such as the Activity AX6, actually have a gyroscope in them as well, which measure the rotation around each of these axes. So this sensor has 6 degrees of freedom. It measures 6 different columns of data. In terms of the activity, it also measures temperature. And depending where the sensor is placed, in our case, it's placed on the skin. It measures the surface temperature of the skin, which we can use, and I'll give you an example in a few slides' time of how we can use that to help us with wear time estimation. And there's also other sensors which measure more things, such as the GT9X from Actigraph, which is a 9 degrees of freedom. It also has a magnetometer, which most of the time is pretty useless, but it's there anyway. In terms of turning these raw data into meaningful values, a very popular method or popular software is GGIR, which was developed by Vincent van Hees in the Netherlands. And this is a piece of software written in R, and it's open source and totally free. And there's been hundreds of publications to date that have used this. And this is basically, it provides you a 5-step process from turning the raw data you saw on the previous slide into summary reports of physical activity metrics and different graphs that you can present as well. This paper, which was published about 1.5 years ago, written by Hiro and others, is a nice description of these 5 steps. So I encourage you to give that a read if you want to know a little bit more about this method of processing, which is probably one of the most popular. And I won't talk about what those 5 steps are, but I can demonstrate a couple of them, which we use in our workflow. But if you want to know more about the actual technical details, such as the algorithms used, coding, all of that type of stuff, we actually have, Vincent and I run this other webinar series for open source software and algorithm development, which is monthly. And if it sounds like something you're interested in, like if you're doing a PhD with accelerometry, it might be beneficial. If you want to be added to the list, the mailing list, you can just send me an email or send Vincent an email, and we can send you some more details. But this is a GitHub page, and if you want to have a look at previous topics, we probably had about 12 or 13 sessions covering everything from machine learning to visualization to teaching accelerometer processing. You can check that out. But moving on, the first step in our processing workflow, well, maybe not the first step, but one of the earlier steps is wear time estimation. And I mentioned before, the temperature sensor on the particular device we use can be used to estimate wear time. So this is an example of temperature, this line here. And at the bottom, this set of data down here is the vector magnitude of the accelerometer. So you can think of it as the intensity. And what we do is we combine these two sources of data to estimate wear time. And the orange is non-wear and the blue is wear time. And it's reasonably clear most of the time. And it's much easier to estimate wear time this way than without the temperature, which is what we found. And in the following visualizations I'll show you in the second half of the presentation, they're based on using 2 accelerometers at once. So one worn on the back and one worn on the thigh. But before I give you some example visualizations of behavior, these visualizations are not so much visualizing the intensity of behavior, but visualizing the type of behavior. And there's a subtle difference. So rather than sedentary, light, moderate, vigorous, what I'll show you is sitting, standing, walking, running, lying, and so on. And in order to do that, I'll just give you a very quick 2 slides of how we estimate activity type from these raw data, as it will help you understand the visualizations I'll show you further down the track. So what we do with the raw data here is we take a big chunk of it. It might be 1 second or 5 seconds or 10 seconds. And we estimate different metrics. It might be the mean, standard deviation, correlations, etc. Maybe for a whole second or 5 seconds. And then we use those variables that we've calculated and we fit a few models, and those models can predict activity type. One of the models we've used reasonably successfully is the random forest. And this is basically a decision tree, which is made up of many decision trees. And you might have heard of a random forest before, but to give you an intuitive understanding of how it works, I'll illustrate. So here we have a graph with two variables, the mean of the x-axis, mean on the z-axis, and they're plotted against each other. And we have a bunch of points. So these might be 1 second intervals or 5 second intervals. And I've colored them red or blue, whether they're sitting or they're walking. And I want to create a decision tree that can classify these two different types of activities really well. So what I might do first of all is using the mean of the z, I might chop it at about 0.5, halfway. And I might say anything below this blue line is sitting, and anything above this blue line is, is standing, or walking below, and above is sitting, the red. And what you'll notice is sitting is quite good in terms of being classified. The sensitivity is very good, but it's also got a mix of walking in there as well. So in order to improve this, we might add another layer to this tree. So we might make another rule here using a cutoff on the x. So anything on the left of this green line would be sitting, and anything on the right would be walking. So this is basically a perfect classification of these fake data, and that's more or less how a decision tree works. And a random forest is obviously many of these averaged. And what do we do once we have this model? Well, we use this model on our data to get predictions of activity type, and then the fun begins. We get to visualize what those look like. So this graph here is 24 hours from midnight all the way to midnight. And we have different activity types predicted by our model. And I should also mention all of these graphs are made in ggplot2, which is, again, an R software. I can talk a little bit about different R packages later. But you can see overnight, this orange chunk is lying. So this would be their sleep period. There's a bunch of sitting during the day and a little bit of walking in the afternoon and evening before they go to bed at 10 o'clock. And that's just one day. We can add the rest of the week, and we can look at differences and patterns between weekdays. So these 4 days here, and weekend days, these 2 days here. So you can see they wake up a lot later in the morning, almost midday on Sunday. So that's an example of a stacked bar chart with different facets for each day. So it's reasonably easy to make, but there's different ways to visualize this type of data as well. And there's different ways to visualize patterns within this graph. So for example, you might be interested in the sitting periods in this graph, and there's clear differences in sitting on weekdays, so these 4 days, versus weekend days. And we can pull out the sitting periods from this graph and look at prolonged periods of sitting, for example. So the more red it becomes, the longer the period of sitting is before it's broken. So these are big, long chunks of sitting, probably at a desk in an office. Another way to visualize this exact same data is using a different coordinate system. So instead of Cartesian coordinates, we use polar coordinates, basically making it a circle. And this is exactly the same two graphs, activity type and sitting, but it's visualized day one is from the middle, and it goes out to day 2 and day 3 and so on. The problem with these graphs is the scale is different on the inside of the graph compared to the outside of the graph. But people seem to like looking at these, particularly. And in order to animate any graph in ggplot, we can just add a few extra lines of code, and we can turn it into an animation using the GG Animate package. And the only thing these are really good for is impressing people when you give presentations, particularly at conferences. But you wouldn't ever really need to animate anything, particularly if you're publishing work. I should also mention that the graphs I'll show you are mostly what we use to understand what we're looking at. We don't necessarily publish these in journal articles. So these aren't graphs from results of a statistical analysis. They're visualizing data that we have in order to understand the patterns and the trends. Slightly different. This is the data we just looked at from an adult, and this is the data from a child. And just looking at these two graphs, you can quite clearly see different patterns. You can probably write a good one-pager on what you observe here. So it probably takes a good 5 minutes to sit and look at this in order to understand what you're looking at. But to give you a few quick pointers, since we don't have all the time in the world, the child seems to wake up about 8 AM every day, and their behavior during the day is much more sporadic. It's much more broken up compared to the adult who has long periods of sitting. The child goes to bed about 9 o'clock most nights, whereas the adult wakes up at 7 AM on weekdays and goes to bed about 10 PM on weekdays, but in the weekend, they are awake until 4 AM in the morning, and then they wake up about midday. This graph is exactly the same as the one I showed you a few slides ago, except the colors are different. In this particular study, it was a workplace study, working with one of my colleagues, Lisa Mackay, and she was interested in work hours versus not work hours and how fatigued people feel during the day. So what we did with this visualization was add a few extra layers to the graph, which are these ones here. So the middle bar is whether they're sleeping, they're at work, or they're not at work. NW is not working hours. And then the top bar is EMA, or real-time questionnaire responses, how fatigued they're feeling or how sleepy they are. And this graph was just used for participant feedback reports. So at the end of the study, they could see their data and what they reported. The next graph I'll show you is what we call an alluvial diagram. Sometimes they're called Sankey plots, and they're used to visualize flows of data from one set of categories to another set of categories. And in this graph, I will bring it up for you. On the left here, we have different activity types for one day. So this is Tuesday, and we have sitting, lying, standing, walking, and running. And this illustrates minute level reallocations between days. So to explain how that works, if someone was sitting at 10 AM on Tuesday, and they were also sitting at 10 AM on Wednesday, this would flow from sitting to sitting. But if they were sitting at 10 AM on Tuesday and lying at 10 AM on Wednesday, it would flow from sitting to lying. So what this is a visualization of is a visual of somebody's routine and how structured their routine is from day to day today. If everything goes across horizontally without any reallocation, they have a very structured routine. But if not, then you'll see a lot of waves. This hasn't really been looked at much in terms of how people structure their day, but you may have heard of the structured day hypothesis, which I guess proposes that the more structured your day is, the better it is for your health and well-being. But there hasn't really been any quality research on that because we haven't really been able to measure it and quantify it. But a good place to start is visualizing these data and based on what you see in this graph, trying to come up with metrics or variables that help describe these patterns. Another example of an alluvial diagram is this graph, which looks at how consistent somebody's sleep and wake patterns are from day to day to day. And the SRI is the Sleep Regularity Index. And that measures how consistent your sleep times and your wake times are each day. So this is quite high. It ranges from 0 to 100. And there's only probably about an hour difference here each day. On the other hand, you can get people like this, who the entire time that they were sleeping on Friday, they were awake the next day. And this is an example of a shift worker who works nights and days. So their sleeping pattern flips halfway through the week. And they have a very low sleep regularity score. And we know that this is not good for several health and well-being outcomes. I think I will skip that one. This is a chord diagram, which is used for illustrating reallocations between 2 time points, for example. It's used quite often these days in compositional data visualization. So how someone reallocates their composition of behaviors from pre to post, or before and after intervention. So for example, active time can be reallocated to sedentary time, or sedentary time can be reallocated to active time. And these are becoming more popular. And there's a nice package in R that you can do circular visualizations. It's called Circlize. And this book explains how that R package works. And this example here is very, very trivial compared to what you can do with this package. You can stack multiple layers of rings outside each other to create some quite detailed visualizations. So just to finish off in my last couple of minutes, I just want to talk a little bit about visualizing spatial data in R. And this is also done in ggplot2, like all of the graphs I've showed you in ggplot. But spatial data is manipulated in R using a package called SF. So what you're looking at here is longitude, latitude, and these are GPS points that someone has collected by wearing a GPS device for about a week. And all of the spatial data I'll show you has been slightly edited to protect this person's privacy. But what we do is we merge this data with accelerometer data, so we can assign an intensity to each one of these points. So the gray ones are non-wear, the green ones are sedentary, and then yellow is light, red MVPA. So this can help us understand spatial patterns of behavior, not simply intensity or type, but starting to provide context to where these behaviors are accumulated. And we can take this a step further by adding in more layers of spatial data. For example, we can turn those points into travel mode based on how fast someone is moving. So here we have green, which is walking, and orange is vehicle travel. We can overlay other layers of data, such as home and school, or green space, parks. And then we can start to calculate how much behavior or how much physical activity of each intensity is accumulated at home, at school, within green space, or any other areas in the neighborhood, such as playgrounds. So on the left is the graph you were looking at before. On the right is the original data points classified based on where they occur. So we can add up all the points that were at home and look at how much of that was MVPA, how much of that was sedentary, and so on. So all of this is done in R as well. And last slide. This is a little application that I put together for ICAM-PAM conference a few years ago, which illustrates this data but interactively. So it's literally Google Maps, and you can zoom in and out and look at hotspots of where behavior occurs based on the density of points. I would give you a little example, but I don't want to go too much over time. In terms of how to learn what I've showed you, all of it is in R, so you need to be able to write some R code. A good place to start is DataCamp, which is online interactive coding sessions. A Data Science book written by Hadley Wickham. And a good book specifically about visualization is Fundamentals of Data Visualization. So this covers what I didn't cover. It covers what type of graph you should use for a particular type of data, whether it's a distribution, counts, time series, how to choose colors, how to choose scales. All of those fundamental principles of visualization are covered very nicely in this book, but it doesn't tell you how to actually make a graph, but this book here does. So hopefully those are some good starting points. Particularly if you're a PhD student, it's good to get into this early if this is part of what you want to learn across your PhD journey. And that's about it from me. Thanks for watching.
Great. Thank you for a presentation, Tom and Kelly. There are questions for those of you. And the first question is for Kelly. And it's from Alison, and where the 3D printed models just related to the physical activity or 24-hour behaviors?
Yeah, thank you, Alison. It's a really good question. These were initially developed just for physical activity and trying to distinguish between moderate and vigorous. But one of the really interesting things that came back from children, we actually did focus groups at the end of the intervention as well. And one of the things that came back from them there was saying, well, it doesn't consider any other types of activity that they do throughout the day. And one of them even commented on how much, if there could be something on the models for sitting time. And I think one of the suggestions from the children was that they could almost have the middle of the sun model could be the size of how long they spend sitting and so on. So you'd almost want that to look into it. And I think one of the children then fed on to that to say, maybe you could have a hole in the middle of that center that would then show how much you were sleeping. So I think that was one of the key findings for me, was just the fact that they could now relate to that we needed to include that in the models as well. So certainly if we were to build on that, I think that's really important as some countries move towards the 24-hour movement guidelines.
Right. And there is also another question from Erika, and question is, are you planning to interview school staff or teachers and parents for use of these 3D tools?
Yes, is a quick answer for that one. So actually involved in this process, which I didn't allude to more so, is when we were doing the initial questions around this, we actually interviewed parents of children of different ages. We interviewed parents as well, teachers as well, and fed that forward. But what we haven't done since finishing it was then get the parents and teachers' perspectives of what that needs to be done. So it's certainly something that we need to do going forwards. But one of the things we always do with this is try and think about anyone who would influence the children, would have a large part in their daily lives. So for us, especially from the educational angle, it's important to embed the teachers' views in it, because if we can't get them engaged in the school, or it's not being reinforced from the parents, then essentially it's never going to work.
And the next question is for Tom, and it's from Bride. And Tom, these metrics are great for visualizing data from an individual. And any suggestions on what works well for cohorts?
Yeah, you're correct. Almost everything I showed you was for an individual participant, but some of the graphs I showed you can also be used for presenting averages for a cohort. So if you think about the chord diagram I showed you, the circular plot with the reallocations between different behaviors, that wasn't from an individual, that was actually from an entire cohort in a study. But you are correct. A lot of what I showed you couldn't be used to represent a cohort. And as I said, somewhere near the beginning, a lot of the graphs I showed you, we don't actually publish. They're just used for us so we can help understand what it is we're looking at. And normally when you present results from cohorts, they would probably be results from an actual analysis rather than of the raw data itself. And that's a slightly different topic about how to present good visualizations of an analysis. But another example that we have used is, imagine like a histogram density curve. We've created those types of visualizations for cohorts, but not anything with the level of detail as what I showed you here. Hopefully that somewhat answers your question.
The next question is also for Tom here. So Kim has asked, what's your take on using visualizations in a participant-facing way, similar to Kelly's as well, for them to be able to use that to enhance their activity levels going forward?
Yeah, that's a good question. And I think that's one of the key strengths of being able to create a nice visualization, is to use it in order to inform participants and hopefully change their behavior. And one of the graphs I showed you, the one from the participant feedback report, that was exactly what that was for. It was to report back to participants an overview of what they had done across the week, with some other recommendations in the report about behavior change and their health and certain strategies they can take. So that graph was embedded within a multiple page report. So that is one example of how that's been used. In terms of specific behavior change initiatives, it might be something like breaking up sitting in the workplace. You could very easily create a visualization for that, similar to the example I showed you, purely on prolonged sitting. So depending what types of behavior change initiatives you're going for, you can definitely start to think about ways how you would visualize that in a way that's understandable by participants, so they can see what they're doing and maybe how to change their behavior.
That's great, thank you. And next question is from Tessa. How much do you use your visualizations for exploring your data and generalizing hypotheses versus creating them based on trying to communicate an already established finding? And that's for Tom.
Yeah, that's a very important question. And if you attended the ISBNPA keynote last year, part of that was talking about hypothesis-driven or hypothesis-generating research versus testing hypotheses in terms of a data science framework. And these visualizations are very, very good for generating hypotheses. So when I showed you the two circular graphs of the child and the adult, and I said it probably takes 5 minutes to sit down and kind of understand what patterns we're looking at. That's what I really like doing, is looking at visualizations and trying to understand what I'm looking at. And based on what I think I'm looking at, I can start to develop new research questions or new ways to measure these behaviors I'm looking at. So hypothesis generation is very much intertwined with creating these types of visuals. Yeah, that's probably all I've got to say about that.
Next is a question for Kelly. So looking at the PEN profiles method for qualitative data, if you use this to feed back to participants, Stephanie was just wondering if it had the same effective assistance in interpretation as the 3D printing models had.
Yeah, thanks, Stephanie. It's a really good question. What we've actually done with the PEN profiles previously is we tend to use them more when we're feeding back to schools, for example, or any companies that are delivering physical activity interventions, as it's quite an easy, accessible way. Government reports as well, for example, we've tended to use them for. We have fed them back in terms of a summary report that participants would get, but this has only actually been for adults. I've never actually thought about doing it for children, which is maybe an interesting way to try and put down on paper and show them what they're thinking and gauge feedback that way. So yeah, certainly some food for thought.
Another one then for Tom. Did you use self-report sleep logs to distinguish lying whilst awake from sleeping on the graphs, or another method from Gemma?
Yep, so it depends what graph you were talking about. We've used different methods of estimating sleep in our work. So there's basically two different approaches, and you've pointed to both of them. One of them is using sleep logs. Or relying purely on accelerometer estimated sleep. And depending what graph you were talking about, we can estimate sleep time reasonably accurately, at least sleep onset and when they wake up. But you're right, it is quite difficult to distinguish between daytime lying, or lying that isn't part of the sleep period, and lying that is part of the sleep period. And it depends on what that daytime lying looks like. If it's quite short lying, I guess it has a bit more movement than what you would get during the daytime or nighttime sleep lying period. It's quite easy to distinguish. Sleep algorithms are improving all the time, and I think we're getting reasonably good at detecting sleep. Actually, in the graphs I showed you, there wasn't any sleep. It was purely lying. But what we have done is also estimate sleep and overlay it with lying. And what we tend to see is the lying period starts and ends more or less when the sleep period starts and ends. That's estimated by the accelerometer. So there are ways to do that, but you're right, it is very tricky.
There is a question from Yane. It's for Tom, and it's about data input. Are there any other kinds of data from wearables that can be used in analyzing types of activity like walking, sitting, etc.? And do you also have any suggestions on how to measure intensity from the data, maybe from the heart rate?
Yeah, so with a lot of wearable sensors, all the information is time-stamped. So whether it's accelerometer, gyroscope, heart rate, or even measuring light, a lot of these sensors measure lux. All of these data streams can be merged together. Same with GPS, it's time-stamped, we can merge it. But then I guess your next question is, how do we measure intensity? Traditionally, what we've done is based on the intensity of the acceleration signal. We've tried to estimate intensity, initially using counts and cut points, which isn't amazing. More recently using raw data, and even cut points on the raw data, which isn't really amazing. But heart rate, as you suggest, is a way to try and improve that. But obviously the limitation is you have to have a heart rate sensor. Participant compliance generally decreases if you have a separate heart rate sensor. But going forward with wrist-based heart rate, and an example that Kelly showed in her presentation is potentially a really good way going forward. But from my understanding of the field, there isn't a lot of software developed already to integrate heart rate and accelerometer data together to estimate intensity better. But it's definitely something that I think we will see more and more going forward. Hopefully that touched your question.
I was just going to say we're almost running out of time, so it was just one very quick last question. One similar to what I had was about engagement with policymakers regarding these different types of data visualization, if either of you have used them or how it's been received.
I'll start with that one then. So I suppose it's quite timely for us. So in Wales, we've just launched the Welsh Institute of Physical Activity, Health and Sport. And this links in with Sport Wales. We obviously have people feeding in from Public Health Wales as well. And the good thing with that is it's a nice way to directly link in with people who then would be making policies. So because it's a fairly recent launch of it, we haven't directly used those visualizations to feed back in, but what we are trying to do is gain an overall kind of baseline, if you like, in Wales, and then think of ways that we could use that by feeding in with the policymakers, stakeholders, for example, that say what kind of data they want, and then we respond to those specific questions. So obviously, if that's a need from their part, then hopefully that data visualization is a really key way to use WIPers as a platform to directly link with them.
I think that's pretty much all we've got time for now. That's spot on 10 o'clock. So I'd like to thank the speakers for coming and sharing their thoughts and presentations with us. It was great. And I think Antonio is going to close us out now.
No, I won't. Just to thank you all, but feel free to close the session, no problem.
Thank you very much all for coming, and hopefully there'll be some more NESI webinars in the future. Thank you.
Thanks, everybody.
Thank you so much.